Good morning, everyone, and welcome back to the Energy Storage Summit 2021. We're absolutely thrilled that we have so many people online this week. And also don't forget, we have more content coming to you next week as well. So now we're going to take a look at thermal storage. So a little bit of a shift in gear for our next presentation. And what we'll do is we have a short slide deck which we delivered, and then at the end of the session we'll have a little bit of a chance for the audience to drop questions into the chat box. So do type them into the chat box at the bottom of your screen, and I will come back on at the end of the session just to go through as many of those as we have time for. I'd like to say a very big thank you, of course, to our sponsors for this week's support, especially our technology and industry diamond partner, Trina Storage, our platinum sponsors, Watlow, EDF, Huawei, Arenco Group, Sungrow, as well as our bronze sponsors. And we're going to hear from one of our bronze sponsors now, Watlow. So I'm really thrilled to be able to welcome Dennis Long and Eric Ludwig to the stage. They're going to talk you through the slides that they have prepared. And if you could share your deck, that would be fantastic. I'll stop sharing mine. And as I said, at the end of the session, I'll come on and go through the audience questions with you. So Dennis and Eric, the stage is now yours. If you could share your slide deck, that would be fantastic. Thank you.
Yeah, good morning, Joe. Thanks for the introduction. This is Dennis Long. I'll be sharing this presentation with Eric Ludwig. I'll be giving you some overview this morning, but Eric will be doing the tough part. Eric, you want to go ahead and let everyone hear your voice?
Yeah, good morning, everyone. I'm Eric Ludwig. I'll be doing the presentation with Dennis. I'll let him start off on the first few slides here, and then I'll take over on some more of the power control content.
Thank you. As Joe said, this morning we'll be talking about thermal storage and a holistic view of that, and specifically we'll be talking about electric thermal energy storage systems and spend quite a bit of time on the control system for those, as that is a major part of electric thermal energy storage and having a successful system deployed. So I'll start with an overview what we call E-test systems, and there are a variety of technologies for E-tests. One would be sensible heat storage, and an example of that is molten salt, and there are other examples as well. Another type is latent heat storage. So in latent heat storage, you typically deploy phase change type materials. Pardon me. And also thermochemical storage, and an example of that would be silica gel water and others. So in these systems that we're seeing today, we're talking about megawatts of power to make the system work. So you could be looking at anywhere from 10 to greater than even 150 megawatts of power needed in the system. So the heating trains, as I show in the top upper right here, they're often configured with multiple electric heat exchangers, and those can be arranged in series or parallel, or various combinations of that. And the control system, as shown in the bottom right hand corner, are often they often need distributed control capability, they need load management capability, and they often even need custom algorithms depending on the system. But all of this is doable with today's technology, as Eric's going to show you. So thinking about the operational scenarios that we have with these E-test systems, they present a number of interesting operational scenarios, and that's why you have to have a very well-designed control system. And so they typically require a number of control engineering experts to assure the uptime needs are met or exceeded for the system as it's deployed in the field. So some examples of those scenarios that could be present, and this is not an exhaustive list, but preheat, startup, freeze protection mode, what might also be called idle mode or low flow. And normally what you're doing there is making up for heat loss. Normal operation, as the system's designed to run normally. A maintenance mode, and that's different. It's not normal idle mode, but power supplies are often changed in that scenario. And so also there could be hybrid situations, hybrid scenarios where there are transitions between the scenarios, and the system has to be ready to deal with those changes in the scenarios. So if you think about the operational scenario considerations, there are maybe 4 primary areas to think about, and those are temperature, because we have different scenarios with different temperature control set points. So for example, you could have the process fluid temperature, the heater sheath and or the tube temperature, the same thing. Looking at those from a durability and thermal degradation standpoint. Also the allowable metal temperature of the containment vessel or the pressure vessel. But in addition, you could also be looking at flow, because with flow you have normal and turn down ratios, pressure, operational mode, and what the allowable pressure drop is, so that you stay within the customer needs, and also power. So available power and warm up and startup modes versus normal mode and an all hybrid in between scenario. So that gives you a pretty good overview of what we're considering here, and I'll let Eric now take the mic and get into the details on this.
Yeah, thank you, Dennis. So what you see here is a basic outline of an ETES system with an electric thermal heater that's helping to heat whatever fluid media, heat transfer media, is going through the system. That heater, as you can see in the upper right-hand corner, can consist of many different forms. It can be a traditional circulation heater that has heating elements or resistive heating elements embedded within it. And those resistive heating elements could be split up into different circuits or steps that can be controlled separately as needed. That's what provides the heat into the system, and then the power for that is distributed through the heater control panels, and then comes off of the grid or comes off of a backup generator, sometimes depending on the operational mode that you may be in. That heat transfer fluid obviously runs through the electrical heating system and goes into the hot media storage area, and then is eventually used in some sort of steam generator to provide the power to the system. So that's just a basic overview. For the rest of this presentation, we're going to focus mainly on controlling this electric heating system and some of the implications and trade-offs that you need to consider when selecting and operating these systems. So next slide, please, Dennis. Thank you. So this is somewhat of an eye chart, so I apologize for that, but I did want to provide the content to you so you could come back and review this. These main 4 bullets are things that need to be considered when designing and controlling one of these electric heater systems. Obviously, safety and reliability is at the top of the list. We also have to understand the overall system and process control needs. We're trying to meet a certain temperature at the outlet of that heater. We need to control that to a precise temperature limit while still maintaining that system reliability. We also have the power management side of that. So whatever is providing the power to that heating system, these, as Dennis said, could be in the several megawatts, maybe several hundred megawatts of power consumed by this electric heater. So power management becomes very important. And then just your overall control architecture. How am I distributing that power to the heater? Since there are many steps and circuits that make up that heater, those also have to be considered. In order to truly optimize the system, all of those have to be considered together and work together to ensure the overall safety, reliability, and process control of the system. So we're not going to cover all of the aspects of this within this presentation. We simply don't have time. However, we are going to hit 2 or 3 of the more important ones in each one of these categories. So next slide, please, Dennis. So let's talk a little bit about the reliability in the thermal cycling. So these big electric heaters have steps or circuits in them that represent a bundle of heating elements, and they need to be switched on and off somehow. So there are a couple of main technologies that are used in the market to switch these large resistive heating branch circuits on and off. And there are different control modes associated with that. You've got your typical on-off. In other words, I'm just going to turn it on sometimes, and I'm going to turn it off sometimes on a regular interval. And then you have time proportional and integral, time proportional, integral, and derivative, which is also known as PID. These are the different types of control modes that are usually embedded in a process controller that can be used to control the temperature of the outlet of that particular heater. And then you have your actual power switching devices, the devices that are turning on and off the actual power going to those resistive elements. Those could be mechanical contactors or what we call an SCR. There is an SSR as well, a solid state relay, but at the amperages that these are pulling, those typically don't come into play. There's also a hybrid scenario where you could have a set of mechanical contactors that control a base load, and then your SCR is used to trim, if you will, an overload of power within a couple of circuits. So let's talk a little bit next about what are the differences in these power controllers and what does that mean to the reliability. So next slide, Dennis, thank you. So when you're controlling the outlet temperature of these particular heaters, the control mode and the type of power switching device you use does come into play. On the far left-hand side, you see a typical on-off control system. The on-off control system will turn power on for a period of time and then turn it off for a period of time, which creates these swings that look more like a sinusoidal signal than it does a good, even, steady outlet temperature. In this particular example, we're using a process set point of 1600 degrees Fahrenheit, which produces an internal temperature in the heating elements themselves of about 2100 degrees Fahrenheit. So the important aspect to the reliability is that internal temperature of the heating element. That's what defines the life of the heating element. The lower that we can operate those heating elements, the more life you're going to have in the system. So in the middle graph, you see what's called an SCR with burst firing. Burst fire is something that switches on and off very, very quickly. You see the time base there at 16.6 milliseconds. That particular burst fire mode helps even out the outlet temperature and also provides a much cooler heater element temperature. You see that 1720. And then finally, on the right-hand side, you see a phase angle controlled SCR. This is where every sinusoidal signal that's going to the particular branch circuit gets cut, if you will, or controlled at a very specific interval to provide a very specific amount of power within that single sinusoidal signal. So that produces your lowest internal temperature at 1680 degrees Fahrenheit. And again, a nice smooth curve. So what does that mean to the overall life? Next slide, please, Dennis. So overall, we've done a lot of testing to understand heater life as associated with these different power switching modes. And you see that the SCR phase angle firing that we saw from the previous slide that had the lowest element temperature to it actually lasts longer than your other control modes within the system. Your SCR burst firing, which was very close in temperature to that SCR phase angle firing, lasted just about as long. However, these large swings, the sinusoidal swings in temperature that you saw with the electromechanical relay or the contactor type control did not last very long. In fact, it was about 10 times less than your SCR control firing circuits. So this is just something that needs to be considered when going through and understanding what type of power control system you'd like to have to control your heating system. Next slide, please, Dennis. So again, another chart here full of words, and I won't cover all of these, but these are just some of the trade-off considerations when going through and understanding the power switching technology that you'd like to use. A lot of it is based on what we call a modulation period. So that's the period, you can think of that as the total time that it takes to cycle something on and off. So an on period plus an off period would equal your modulation period. And the longer that modulation period becomes, the more time that you can potentially have your heater on or off within that time. But that also then impacts the overall life in the temperatures that heating element is seeing. So a lot of this power switching method up here has to be considered with the modulation period to understand the total life of the system, the operability of the system, and then just your control system response time. So if you have a very long modulation period, you may not be able to control your system to a precise temperature. Shorter modulation periods allow you to switch that power on and off faster and have a better response to transients or other items that may impact the temperature of your system. Your operating mode comes into play as well. So in some operating modes where you don't have a lot of transients, on-off control may be okay for the operation of your system. Whereas if you have an operating mode that has a lot of transients in it, then you're going to want a faster switching speed within your control system. So all of these trade-offs have to be made and considered when looking at your overall control system and the power switching technology that you'll need to use. Next slide, please, Dennis. So this is an overview of a typical heating system that might be deployed in one of these applications. And really, it's just showing the difference between a centralized control system and a distributed control system. So on the top graph, you see more of a centralized control system where there's a single control panel communicating to a DCS system. That control panel then sends signals over to the middle power panels. Because these particular heating systems are so large, typically you have multiple power panels that feed the heaters within the system. So you might have a 5 megawatt panel feeding a train of heaters that may be 15, 20, 30 megawatts of heaters. You may have multiple trains of those heaters that are serving in the system. So you basically have a multitude of power panels and a singular control panel. The DCS just talks to that control panel, and then the control panel could have any various types of controllers. It could have a PLC, could have a different type of temperature process controller in it. Those would then send the signals over to the power panels. The power panels would house those power switching devices we just talked about, either the contactors or the SCRs, and those would switch the power over to the heaters. In the bottom system, we have more of a distributed control system where the DCS talks to all of the power panels, and the power and the controls are kind of combined together within those power panels. In that particular system, your DCS is talking to almost each one of the power panels independently. This has some benefits to it with regards to reliability of the network. In your centralized control system above, everything goes through a single control panel. Something were to fail in that control panel, you likely lose your entire heater field. In a distributed control system, if one of the communications or one of the circuits, so to say, goes out, then it's just that circuit that goes out. We still have control of the other circuits in the system. So again, there's positives and benefits to each one of these that need to be understood. Dennis, next slide, please. And so those are some of the trade-offs that we would have to make when considering it. I'm going to talk a little bit about the process control types. We talked earlier about the PID, the integral. These are just kind of block diagrams of some of the different types of controls that may be used in the process controller itself. So you see the gray box represents the heater or the vessel. It's got an inlet where the fluid comes in and an outlet where the heated fluid comes out. You're typically measuring the outlet temperature of that fluid to make sure it's well within the process parameters that we need. A typical PID loop would take that outlet temperature, compare it to a set point value, and then just turn on and off the heaters to ensure that that outlet temperature is being met. And that's how a traditional feedback control loop would work. In the center diagram, we have what's called a cascade PID control. The advantages of this is that it puts an additional sensor inside of the heater or the vessel itself, and you're actually controlling two loops. One is the outer temperature, so that the outlet temperature is met, but the other one is an internal temperature. And typically that's on like the heater sheath itself to ensure the reliability of that heater and also ensure the reliability of the fluid passing through the heater. In that particular case, you're preventing the fluid from overheating and preventing the element itself. So it controls not only the outlet temperature, but also controls the inside temperature within the actual heater itself to ensure certain limits aren't being met. So there's some advantages of the cascade PID control loop right there. The last one in the bottom side is what we call a feed-forward scaling system. And this one is really useful when you're going through transient type responses. A lot of times you may have to increase your fan or pump speed, which increases the velocity of the fluid going through the system. There's a latency sometimes of your heating system to react to that. If we're just using feedback control, you have to wait for that fluid to take effect on the sensors in the system. But if we have a sensor on that fan and pump speed that we can put into the control system, then we can anticipate that additional heat load need and start to react to that quicker. So we call that a feed-forward scaling system, and that's typically used, like we said, in those modes that we would expect a transient response to occur. So all of these can be used, and in fact, all of these can be used in the same control system and just switched by operating mode. So Dennis, next slide, please. So again, some of the trade-off considerations here associated with the control mode and the operating system. We talked a little bit about understanding which operating modes you would use in each control mode. If you got more of a steady state operation, then you can use more of an on-off type control system, and a straight PID loop may work. Whereas if you've got a lot of transients in a particular operating mode, then you want to use kind of a feed-forward PID system. So these control modes also have influence over transient performance. The modulation period gets into effect here as well, because you want to be able to control the outlet temperature with a precise control and not have it swing. So again, I'm not going to hit on all of these. We can have some Q&A after the session if needed. So next slide, please, Dennis. So let's talk a little bit about power management now too. So obviously a lot of power being consumed by these large electrical heaters that need to be switched on and off. What you see in the upper right-hand corner is a depiction of how the electrical signal or the power signal is switched. So when it's on, which is represented by the T on in the graph, you're getting full power into the system. And when it's off, it's obviously off and you're getting no power. The T on plus the T off is represented by the TSYC, or the T cycle, which is what we call the modulation period. So that's the control period that we work within. And we can manipulate the time that the power is on versus the time that the power is off in there to supply a certain effective power or effective heat into the fluid. So what you see in the middle graphs right there, kind of the green graphs, is on the left-hand side, where you have a 100% duty cycle. In other words, we're firing this particular circuit all the time. It's 100% on. In this particular example, we've got 500 kilowatts in that circuit being deployed into the system. It's 100% on, so your effective power being consumed and the effective heat going into the system is 500 kilowatts. That's also the instantaneous power that you are consuming. On the right-hand side, you'll see that we start to cycle this. This is a 60% duty cycle graph. So it's on 60% of the time during that modulation period and off for 40% of the time. So for 0.6 seconds, this signal is on, and for 0.4 seconds, it is off. This has a modulation period of 1 second to make the math easy here. So while this is on, you can see that the power, the instantaneous power that the system consumes is a full 500 kilowatts. But the effective power over that 1 second period of time is actually only 300 kilowatts. And that, because of an electric heating element, is the actual power that will be placed into the heating system itself. The heating system will see that 300 kilowatts. However, the instantaneous power when that's on is 500 kilowatts, and that becomes important. You have to understand and analyze your feeder system to understand whether it can withstand that instantaneous power load. So let me give a quick example of that. Next slide, please, Dennis. If we have a 12 circuit heating system, each one of those circuits 500 kilowatts, and we're firing those circuits at 50% of time, and we have no coordination with those circuits. Each one is allowed to run its own control loop independently and fire on and off independently. What you see by the kind of green and white checkerboard pattern in the top graph is the on-off cycles. Every time it's green, that particular circuit's on. Every time it's white, that particular circuit's off. So I'm using a 1 second modulation period, and I'm showing you 3 cycle periods here. Just very independent firing, each one firing at 50% of its total time. So the overall system in the bottom graph here, you see these large power swings. If you add up all of the green on the top graph, you get about 5 megawatts of power being generated in the very first portion of the modulation cycle. And then the very next portion, you only see 1 megawatt. So you're swinging this power profile by 4 megawatts every other cycle. Now, effectively, that averages out to 3 megawatts of power being delivered into your overall system. So your system is still seeing the 3 megawatts it might need at that 50% duty cycle, but your feeder system is swinging by 4 megawatts within that. And that can be very detrimental to your feeder systems. Next slide, please. So there's a technique that can be used to optimize the load and level the load. So we call this a power management load optimization algorithm that can go in and actually sequence the on-off cycles of each one of these steps and circuits to ensure that you are leveling the power within there. So it basically takes all of the circuits themselves, understands the duty cycle needed, and then aligns the on-off periods of those duty cycles so that we don't get these very large swings in power within the grid. So you can see this has been fully optimized. This is an ideal optimization scenario where all 12 of the circuits are working together. They are actually talking to each other through the SCR algorithms. And their on-off times are synchronized. And you see the average power then on the resulting graph below states basically that you get your 3 megawatts, but it's all leveled now. So next slide, please. So that has to be considered as well when you're looking at this. That's kind of the power trade-offs of this. And again, we have to look at the overall operation of the system, your peak power draw, what you have available as a feeder system in order to control this. And particularly if you are limited in some of your operating modes as to the feeder power supply, that has to be taken into consideration as well. And we have to manage that power load overall. So the bottom line here is your consumed power has to be less than your available power, and all those trade-offs need to be optimized for the system safety and reliability. Next slide, please, Dennis. So this is just a summary of all of those. You know, we're talking a little bit about the modulation period. You have a controller scan time as well that's in there. You've got the modulation period to think about. And then you have your thermal response time, the time it takes the heat to get into the system before the sensor actually senses it and feeds that back to the controller. All of those have to be taken into consideration. The safety, reliability of the system, the heater design, the process control design, and then the power utilization and management all need to be taken into consideration. And it affects not only that heater design, but your total system design and your total performance. So the bottom line is your ideal system is one that accounts for all those trade-off considerations and optimizes the design between the heater, the sensors, and the controller and power panels, not just within each one of those individual components. So last slide, please, Dennis. I think I'm going to turn it back over to you to wrap it up.
Yeah, thank you so much, Eric. And I'll quickly go through conclusions here and turn it back over to Joe for any chat questions that are out there. So electric thermal energy storage offers exciting technologies that can allow us around the globe to provide 24/7 dispatchable power from renewable energy sources. So that's pretty exciting. Electric heat exchangers for e-tests may be configured in a variety of large megawatt scenarios, as we've shown. And most importantly for this presentation, the control system design is extremely important to assure the system can be well controlled within the variety of scenarios that we've shown for the operator to achieve their performance requirement needs. So electric thermal systems consisting of electric heat exchangers and a control system. The technology today is very capable of the flexible operation required for e-tests. And with that, Joe, I think we're doing okay on time here. I'll turn it back over to you.
Hello, thank you very much, gentlemen. That was a great presentation. I'm just going to come back to full screen for the video so that we can go through the questions. So I have seen a couple of questions come through. Audience members, we're running a little bit over, but we do have time for questions. So if you have any further questions for Dennis or for Eric, do put them into the chat. So first question comes from Paul DeFays, who asks, what is the round trip efficiency of, for example, a molten heat storage system?
Yeah, so I can speak. I can speak specifically to the electric heater side of that. So the power that comes into the electric heat versus the power that gets transmitted into the fluid itself. There are losses in the system, as you might suspect. Within the power switching devices themselves, there are losses. You know, we typically see less than 5% losses in the overall system from the power generation feeder into the actual media itself, the thermal response of that. The losses in the rest of the system within your energy storage media and in your hot tanks and the cold tanks, I can't speak intelligently to that. Perhaps Dennis, you might know a little more about that.
No, I think we would leave that to the tank manufacturers on that side of it.
Yeah, so the thermal efficiency, the electric heat thermal efficiency is very, very good in these systems because of the electrical resistive elements in the technology of those electrical resistive elements. The power provided gets transmitted into the thermal media, minus just the electrical losses that are due to the current carrying components in there. So they're very, very efficient.
That's good, thank you. And there's a question here from Tien Ming Yoon, who wants to sort of focus a little bit around concentrated solar power. So Tien rightly points out that a lot of the focus over recent years has been on solar PV. So does Watlow kind of work with CSP projects? And he would love to hear insights that you might have about CSP. Are there any kind of developments that you're aware of that have happened in the industry? And how might a project compare with solar PV?
Yes,
it's a bit of a three-parter, I think.
Yeah. Yes, I think they're asking about, do we see trends to more thermal solar energy storage rather than just PV and battery? And yeah, I think your publication even you can track those trends around the world fairly easily with some of the major trade journals. But yeah, I think people are looking at combinations of technologies. So not just PV and battery, but even hybrid combinations. I think that thermal energy storage is going to become a much bigger picture of that for large energy scenarios going forward, because it allows a 24/7 dispatchable situation, whereas most batteries are set up for a 1 or 2 hour transition to.
And I guess it's also very, very location specific. So Tien, I'm not sure where you're kind of listening from, but obviously not every location.
Yeah, I think the thing we have to consider with thermal energy storage is I can connect it to any renewable energy source and store that energy, whether that's a wind turbine or even if it's PV. And so that's one of the beauties of it. So it doesn't have to be connected to just concentrated solar power.
Makes sense. And so they were all of the questions that we had on the panel today. So I'm going to draw the session to a close. Just to remind the audience that on the Events Air platform for the conference, you can see the full attendee list, you can message other delegates, and you can arrange one-to-one meetings with other people on the platform. So it might be a good chance to follow up with Dennis, Eric, and any of the other team members from Watlow if you have more questions for them. So that's just on the Events Air platform, and there's a link that says Member Hub. That's where you can see the attendee list and do all those things that I mentioned. There's also an exhibition hub. So again, if you'd like to sort of see further information on any of our sponsors or exhibitors, that is also available to you. I know that a lot of sponsors provided white papers and reports and other materials for your consumption. But Dennis and Eric, thank you very much for the presentation today. It was really interesting to hear a little bit more about thermal. I think it's definitely underrepresented at some of these events. So thank you very much for joining us, and hope to see you soon face to face at the next conference.
Yeah, that would be great. Thank you, Joe. Appreciate it.
Thank you, Joe.
Thank you both. Have a lovely day. Take care.
You too.
Bye-bye.